Hello, everyone, and thank you for joining us for the final lecture in our series on Radio This IAP. Before we begin, I'd just like to thank all of our speakers who have joined us, and also to thank some of our alumni and donors. Over the past month, the club has made enormous headway towards its fundraising goal for our VHF station, and we owe a lot of you a great debt for that. For those who aren't aware of the details or haven't contributed yet, we're currently fundraising for the renewal of our amateur station up on MIT's Green Building. You can find more details on our website, wmx.mit.edu. But with that, I'd like to introduce our speaker, Dr. Ruonan Han. Professor Ruonan Han earned his bachelor's degree from Fudan University in 2007, his master's in electrical engineering from the University of Florida in 2009. And in 2014, he earned his PhD degree in electrical engineering and computer engineering from Cornell University before joining the faculty here at MIT. His research group here at MIT focuses on RF to photonics integrated circuits for spectroscopy, imaging, quantum sensing, and broadband communications. Professor Han is a senior member of the IEEE and the IEEE MTTS Distinguished Microwave Lecturer. In 2017, Dr. Han received the National Science Foundation Career Award, and 2019, he earned the Intel Outstanding Researcher Award. With that, I'd like you to give a warm welcome to Professor Ruonan Han. Thank you.
All right, thank you very much. I guess the most important thing right now is, can you hear me well? Nice. So my name is Ruonan Han. I'm right now the Associate Professor of ECS Department. And today I'm going to talk about chip-scale terahertz circuits and systems. In case you don't know about terahertz, it is normally defined to be the frequency between 100 gigahertz to 10 terahertz. So we are talking about a span that is 2 decades long and absolutely large bandwidth out there, especially all of us, we are from the radio community. And probably last year you start to hear something about terahertz. For example, this black hole imaging where Dan is working in this haystack observatory. They are working on this. Those are actually done in the terahertz range. Okay, I think 230 gigahertz. And also now that we have intensively been talking about 5G communications, people start to think about 6G. Okay, and the terahertz spectrum could be an option, even though that's still controversial. So that's terahertz, and absolutely, it's coming up, and it's going to be a very exciting topic. Today in here, instead of talking about those research areas, I'm going to talk about how we can realize terahertz signal generations, detections, and build some really large microsystems using very low-cost chips. And by low cost, I mean, silicon CMOS chips, okay? So how can we couple these two domains, very different domains together? Before talking about that, I would like to give you some very interesting history about terahertz, okay? So this work is probably the earliest work, at least, to me, this is the earliest I can find that relates to terahertz, okay? So in this work, published in almost 200 years ago, basically the researchers have developed 160 gigahertz spark gap oscillators. So you basically create some avalanche breakdown inside the air, and you use that breakdown to create some negative resistance, and then you can build an oscillator out of this, okay? It's amazing. 100 years ago, people have already been able to generate 160 gigahertz signal. And in order to detect that signal and also measure the frequency, they use microwave wire detectors and interferometers, okay? So all these devices could be done 100 years ago. So sometimes, my students complain about designing terahertz circuits being too hard. I show them this example. But I think what's more interesting is, these two sentences that are listed in the abstract of the paper. So basically, the authors say that there is doubtless little need of any further experimental proof of the essential identity between heat waves and electric waves, yet, for the sake of completeness, further effort to bridge the existing gap between these two spectra seems warranted. Okay, so this is probably the very first time this terahertz gap concept is introduced. And back then, what you can see is, 100 years ago, people really don't have a very clear mind regarding what this wave could do. Instead, they just want to fill the gap to fulfill their scientific curiosity, which is actually something I really appreciate. So this is what's happening 100 years ago. And what I would like to show you is that after 1 century, right now, all these components, right, now we can integrate them into a very low cost and a very small silicon chips. Okay, for example, in this example, produced by my own group, we are able to generate 10 antenna-fed transceivers operating at different frequencies between 220 gigahertz to 320 gigahertz. And we integrate all of them together inside a very little CMOS chip. And they absolutely have a very clear function out there. Okay? So this very large integration enables us to now not only just explore more on this frequency range, but also start to utilize some of its nice features to enable some nice applications. So I basically call this the dawn of a new terahertz era. Because if you look at what is happening right now, people start to demonstrate quite some applications, like people use terahertz spectrometers to analyze the interstellar dust composition. They use terahertz transceivers to do some security scanning, and also researchers use the terahertz transceivers to do point-to-point wireless communications. And if you look at the enabling technologies, the hardware technologies behind these applications, they are still based on some quite expensive and bulky hardwares. For example, quantum cascade laser, where you have to cool the device down, or very expensive vacuum electronics, or compound semiconductor discrete components. So on the other hand, though, if you look at what's going to be happening in the future, I think it's going to be very exciting that, for example, we are going to deploy a large number of wireless access nodes in probably every room, okay? And then our mobile device can communicate with these access nodes with very, very high speed. And also we can use terahertz spectrometers, which now have a very small form factor to, for example, analyze our breath and to do some very portable, imaging tasks. And also we can do, medical imaging, and also to transmit very high speed data across chips, across different hardwares. But if you think about the new requirement, okay, for all of these new applications, well, first of all, the cost and size of these devices have to dramatically drop. And also at the same time, these applications require very high complexity systems, okay? So probably the only possible solution to all of these requirements is to build these terahertz hardware on very small and very low cost CMOS chips, even though it's pretty hard. So if you look at the advances in the past 10 years or maybe 15 years, people have already achieved very good success in terms of terahertz imaging arrays. This is kind of like the CCD arrays behind the lens of your camera, but they operate in the terahertz range, and people can build arrays of these terahertz wave detectors on the same chip. And for example, the frequency can go up to 0.7 terahertz, 1 terahertz, and sometimes it can go up to 5 terahertz or even 10 terahertz. And if you look at the sensitivity, which is quantified by noise equivalent power, it's also a very decent number, okay? Even compared to the more expensive technologies like room temperature bolometers and the other 3.5 semiconductor diodes. So this is a very nice application of CMOS chips inside terahertz, which is square law detections. However, there's a very big party pooper throughout these years, and that is the speed of the silicon devices. So if you work in the device area, you probably know that silicon device has never been famous for being fast. They're actually slow, they're actually noisy. And here I show you the measured cutoff frequency of different CMOS and silicon germanium devices across different technology nodes. So this research was done by Georgia Tech. And what you can see is, number one, the cutoff frequency of these devices is really not that high. Okay, so when we are talking about terahertz, we are talking about operating in a few hundred gigahertz. But the cutoff frequency, which is the theoretical limit of how fast these devices can run at, is about 200 gigahertz. Okay, so you have this fundamental limit out there. It seems that we just cannot run above this. And the other pretty depressing fact, especially was really depressing to me a few years ago, is if you look at the scaling of these devices. As we know, as you get the device smaller and smaller, for digital circuits, you just get faster and more efficient operations. But if you take a look at the cutoff frequency of these CMOS devices, they actually go down. Okay? So the RF speed of these devices really doesn't scale with the device. So it seems to be a really hopeless future. And indeed, if you take a look at the early work in this field, where people try to generate, instead of detect, they try to generate terahertz wave using CMOS chips, what you can see is, for example, this one, the radiated power is only 20 nanowatt. So, what can you do with nanowatt of power, okay? This one is the same, 25 nanowatt, okay? So this indirectly verify our previous claim that, silicon devices are slow, and they don't seem to be the good candidates for terahertz operations, all right? So that was, essentially the status roughly, 15 or 12 years ago, and we started from there. Okay, so in the next few slides, I want to show you how we can sort of indirectly avoid these problems of the silicon devices and dramatically increase the output power of these chips. And then we start to build large-scale systems to make some applications possible. Okay, so first of all, I will talk about some general approaches. I don't want to go to the details, but just to give you a feeling about what could be done with these devices. And then I'll give you a few examples regarding how we can design large-scale terahertz arrays to generate power and also detect the signals. But I think the next very exciting topic for this field in general is to what I call fill the gap. Okay, you probably have already heard about this filling the terahertz gap, and this doesn't seem to be a very new topic. But here I would claim that, in case you don't know about terahertz gap, it is referred to the very low performance of terahertz components in comparison with the microwave counterparts and also the infrared counterparts. Okay, by performance, normally people refer to the generated power. So people have been trying to fill up this gap for decades. But here, when I talk about the filling the gap, I really refer to a gap that is two-dimensional. Okay? It's two-dimensional. So rather than filling a gap at a component level where you want to get more power or more sensitivity, one general problem of this field is that people still don't have a very clear mind regarding what kind of applications that these components can enable. Okay, technically, generating power has already been very hard. We normally don't take the extra step to think about what could be done if we have those components. Okay, and then the other thing is, suppose we have some applications, and then how do we design systems to enable these applications? Shall we just do an extrapolation of the existing radio frequency or millimeter wave frequency systems and just make them smaller and faster? Or shall I do something that is completely different? Okay, so this is the gap that I refer to, and hopefully in the second half of my talk, I can show you how we can try to use these CMOS chips to fill up this part of this two-dimensional gap. And with that, I would like to just show you two examples related to the wave-matter interactions in the terahertz range, where the terahertz wave can create the rotation of molecules, and we turn that into a gas sensor. So now the chip can literally smell, and also another molecular clock, where the chip can count the rotation of a certain molecule and translate that counts into a very stable output frequency. All right? So let's see how we can increase the performance of these devices. Let's get back to this party pooper. Okay, as you probably still remember, speed is very low. And if you translate that speed limit into the design of an amplifier in this frequency range, if you just plot what's called the available power out of an active device, you can see that theoretically, in low frequency, you can get very high gain, but this gain dramatically decrease until when you reach the Fmax or this cutoff frequency, now your theoretical power gain becomes 1, okay? So the problem is, number one, you are not able to design any amplifier above this limit. And number two, even if you take some back off and design your amplifier here, the available gain is really, really small, okay? Making the amplifier still very impractical, okay? Of course, you can say, okay, you know what? I can design an amplifier below my cutoff frequency with very little gain, but then I can cascade a lot of amplifiers together, okay? And then I can still get a lot of gain. Indeed, I mean, people try that. For example, researchers who work on indium phosphide high-speed transistors, number one, the cutoff frequency of such a transistor is very high, but their goal is also very high. They want to design amplifier at 1 terahertz. Okay, so each stage of the amplifier still provides you just very little gain, but they can cascade, for example, in this case, 10 stages together in order to get 10 dB of power gain. Okay, so you can count and do your math and see how much dB you have out of a single stage. Okay, so this is the trick that you can probably play, but I wouldn't say this is a very good trick. Okay, so what else can we do? I will skip some of the details in here, but the basic idea is when we learn about analog circuit design, we learn about positive feedback and negative feedback. And one thing that we normally don't like is positive feedback introduced into an amplifier or circuit, and that starts to cause instabilities or oscillations, right? So you want to design an amplifier, you don't want to end up getting an oscillator in your circuit. However, in here, we show that if you intentionally introduce some feedback, so you collect some power from the output, send it to the input with the correct phase and amplitude, and you control that precisely, you control that well, you can dramatically increase the gain of a certain device, okay? You still cannot overcome this fundamental theoretical limit. So the maximum frequency you can operate is still the same. But below this, when you take the back off, you get dramatically higher gain. Okay, so once you have that, now you can get pretty practical amplifier out of smaller number of stages. So that's one thing that normally people play nowadays in order to use these low-speed silicon devices to design circuits at around 100 gigahertz and 200 gigahertz. And then on top of that, people can also extract the harmonic signals out of these devices. So imagine that you design an oscillator at, for example, 100 gigahertz. The output waveform of this oscillator is never a perfect sinusoidal wave. Okay, and as a matter of fact, you can greatly distort the output wave so that it contains a lot of harmonic components. And then you filter your output, and you select a certain frequency component out of this, and then you can get very high frequency. Okay, for example, second order harmonic will be 400 gigahertz. If you get the fourth one, it becomes 800 gigahertz. Okay, so this is also a very common trick that people play. But in order to play that trick, there are still quite some things that need to be done. And if you learn something about device physics, you probably know that these transistors are based on the transition or transportations of carriers inside semiconductors. Okay, and this transportation really takes some time. It's not a long time for these devices. It's like picosecond, very short time. But if you think about one period of a 300 gigahertz signal, okay, 1 picosecond is really, really large. Okay, so because of that, the transistor normally cannot really follow your input signal at very high frequency. But one trick that you can do is you can create a network around this transistor and sort of compensate for that delay. okay? If the transistor really cannot follow, the output of the transistor really cannot follow the quick variation of the input, you just, also, for example, the current at the output cannot follow, you intentionally also slow down the variation of its output voltage so that the current and the voltages are always in phase. And as we know, once we have a voltage and a current which are always in phase, then that means that the device can generate some real power, okay? So this is another trick that people normally do. And after all of these optimizations, now if you use the same process, for example, in this case, it's still 65 nanometer CMOS process, as you can see from the previous cases. What we see now is, with these device optimizations, now the output power could be as high as 1 milliwatt, okay? This is the radiated power out of 8 elements from a single chip. And if you do the math, this one is way higher, okay? Orders of magnitude higher than this tens of nanowatt work that was done before, okay? So since the publications of this work, people start to gain confidence that, okay, you know what, maybe these silicon chips are able to do something practical. And here's another example. That one was operating at 260 gigahertz. This one was operating at 320 gigahertz. Okay, we can build an array of those. And instead of letting these oscillators to run freely, now you can even build a phase lock loop at, in this case, 160 gigahertz, and do the injection locking of all of these oscillators. So now you do not just have a high power output at 320 gigahertz, you also phase lock them. Okay, so you can precisely control the phase and also output frequencies of this terahertz wave, which is a very important feature for future applications like radars and communications. If you learn something about phase lock loop, you probably are very familiar with a graph like this. So here we show you that without the phase locking, the output spectrum of this chip is pretty broad, okay, meaning that it has quite some phase instability. But then you turn on this on-chip phase lock loop, you have a very nice and sharp output spectrum, meaning that now the phase is stabilized. Okay, and this is actually also the record power so far in silicon devices. In the silicon now you can radiate 3.3 milliwatt of power. Okay, the other nice feature that I would like to emphasize for these devices is, suppose you have, in this case, 16 elements, and they work collaboratively. They generate the same amount of power, they generate the same frequency, and even the same phase. Then you start to have interference in the free space, okay? This is kind of like a laser, that you have a large array of devices, and they all have the in-phase operation. Now the output wave becomes collimated, okay? So instead of shooting the wave to all kinds of directions, now you start to point the wave towards a certain direction, okay? And this is normally how people operate their, for example, phased arrays. And indeed, in here, if you look at the measured output beam, you can see that now the beam width of the output radiation is really narrow. And because of this focus, because of this concentration of wave, the EIRP, or effective isotropically radiated power, is as high as 180 milliwatts. So what does this mean? This means if you want to replace this chip with an isotropically radiated signal source, and you want to generate the same amount of wave intensity in the far field at somewhere, that new source needs to generate 180 milliwatt of power, okay? So now you don't need that because you collimate the beam to a large extent. So what is the opportunity going forward? I think it's very exciting and also very challenging. So here I show you some estimations regarding the calculation of, suppose I have a 10 millimeter square chip area, and I fill this area with all terahertz sources, okay, with their antennas, as you have already seen. And if you learn something about, radar arrays and phased arrays, you probably know that, in order to create interference of these waves, but without having side lobes in different directions, okay, so that you can have a very good collimation of the wave. The distance between these sources should be half wavelength, okay? And obviously, this also scales with different frequencies. So suppose I have 10 millimeters square active chip area, and also if I keep the pitch to be half wavelength at different frequency, what you can see is at 10 gigahertz, inside this chip area, I can only have one source with its own antenna, okay? So of course, each source can generate a lot of power, but the output beam is pretty broad because you have only one element. And now if you operate in the millimeter wave range, say 60 gigahertz, in the same area, now you can have more antennas. For example, at 10 gigahertz with 10 millimeter square area, you are able to get roughly, in this case, 10 elements, okay? So now you have 10 elements, you can have a larger output collimation, and in this case, you can get like tenths of degree of output beam width. And now, if I operate in 300 gigahertz, and this is just the chip that you just seen, with this density that is the same as this chip, and I keep this a pitch of half wavelength, what you can see is at 300 gigahertz, or the low end of the terahertz range, now I'm able to integrate roughly 100 elements, 100 radiators on the same chip size, okay? And because of this more radiator integration, now the beam width will be as small as 10 degree. So now we are talking about an output beam of this much, okay? Why do I care about this? If you think about, for example, radar imaging, instead of detection of a lot of people simultaneously on the road and without knowing who's who, now you can really direct a very small beam and point to them individually, okay? So you greatly increase the resolution inside your sensing. So this is really important. And then here's the question. If I can increase the frequency more, if I'm really greedy, to 1 terahertz, now inside the same area, if you do the math, now you're able to integrate 1,000 elements inside this little chip, roughly 3 by 3, okay? They all have their own antennas. They all operate together coherently. And now, if you look at the output beam width, it's only 2 degrees, 3 degrees, okay? So now we are literally talking about a silicon-based terahertz laser that generates a very narrow beam, and you can do very high resolution imaging, okay? So that's the holy grail, or one of the holy grails of the field. However, this is extremely hard, and that's because of this what we call half wavelength dilemma. And what this says is, I need to keep this pitch of half wavelength, but in 1 terahertz, half wavelength is actually a very small size, okay? Especially in this dielectric environment where you need to divide your wavelength with square root of a dielectric constant. This size is about only 200 micrometer, okay? So it's a very small size, but at the same time, you need to fill in a lot of elements inside this little space. For example, if you want to truly generate a 1 terahertz source out of the current silicon devices, then the only thing you can do is that you run an oscillator at 250 gigahertz, and then you extract the 4th order harmonic out of this signal. You make it really distorted, and then you extract the 4th order harmonic out of this. And then you also need to build an antenna at 1 terahertz in order to radiate, okay? If you know something about antenna design, normally the dimension of the antenna is already half wavelength, okay? And also on top of that, you also don't want to radiate the fundamental 2nd order and 3rd order harmonics, so you probably also need a filter to take the other things out, okay? And you have to integrate all of these things together inside this very little space, okay? So that's the challenge. That is why, people find it very hard to generate a very large density, high density scale terahertz radiators in this kind of a frequency. So one possible solution is that instead of building these functional components one by one and then try to squeeze them together, how about we just build what's called a multifunctional structure okay? This is like an electromagnetic structure, and this structure simultaneously perform all these tasks together, okay? So it can perform the radiation, it can perform the filtering, it can do the oscillation, it can do the harmonic generation. That would be nice, right? So this is the, on top of the device optimization that I just talked about, this is actually another thing that, the field is trying to do in order to overcome all these problems. And I just give you a very little portion of this effort to kind of show you how this thing can happen. For example, in here, we want to generate a 1 terahertz signal out of a pair of 250 gigahertz fundamental oscillators. And what can be done is, normally I use a pair of a differential 250 gigahertz signal oscillators to drive a pair of what we call slot antenna, okay? And this slot antenna also behaves as the resonator for this 250 gigahertz oscillator, which means that the length of each slot should be a quarter wavelength at fundamental frequency. In here, it's 250 gigahertz. So then you have the resonance, you have the oscillation, which is what you want. However, if you look at the field distribution inside these two slots, which is shown here, then we have some problem. For example, at second order harmonic signal, okay, let me take this out, okay? So for the second harmonic signal, we see that the electrical field on the left side and right side, they are in phase. So that means this resonator designed for the fundamental oscillation at 250 gigahertz actually radiate at 500 gigahertz, which is not what I want, okay? So that's really bad. And also, if you look at the radiation or the field distribution at the desired 1 terahertz frequency, this electrical field will cancel this field, and this one will cancel this. So you really don't have the desired radiation you want, okay? So this thing essentially designed at the wrong frequency. And also, if you think about putting this kind of an element together side by side, you are also in trouble because let's say I duplicate this part to here, and now if I calculate the center-to-center pitch between these two elements, that's going to be lambda over 2 at the fundamental frequency, okay? That's too large for the previous half wavelength pitch that I was talking about. And then, once you combine the wave together and have the interference, you will shoot out different side lobes to different directions, which is bad. So what can we do? This is a very simple but very elegant trick. Let me fold this slot at 1/4 and 3/4 points, okay? So that now I form something like this. So it seems that nothing changes. For example, if you look at the field distribution inside each slot for fundamental frequency, of course, it should be the same, okay? But now if you look at the field distribution inside this horizontal slot and also this horizontal slots, which is shown here, you can see that this part cancel this and this part cancel this, okay? So now these horizontal slots, they don't radiate at second order harmonic signals. Okay, third order, the same thing. And now if you look at the field distribution for the fourth order harmonic signals, this section, this section, this section, this section, they're all in phase. Okay, so this is just a very simple geometric flip. But now you have all your desired frequency at 1 terahertz, so this fourth order harmonic signal can directly just jump out of the chip. Okay, so now if you think about this whole thing, I just do this simple folding, but now this structure gives you resonance at fundamental frequency, filtering for all these fundamental second order, third order components that you don't want, and also radiation naturally at the fourth order harmonics. Okay, so now this becomes very efficient, and also it gives you quite some savings for the space. All right. So because of this, oops. So because of this, we actually designed the chip using a silicon germanium BiCMOS process, and we put a lot of these folded slots driven by transistors together, okay? And the end result is inside a 1 millimeter square area, we are able to integrate 91 elements, 91 antennas. They are placed side by side, and they all radiate together with a coherent phase relationship, and you kept this half lambda pitch as what you wanted. Okay, and now you can nicely insert this figure into this projection of this graph, and the density-wise, it matches our prediction very well. Okay. Of course, the size of this one is not 10 millimeters square, it's 1 millimeter square, but in terms of the radiator density, it's exactly the same. Okay. This one kind of show you how we do the experiment in our terahertz circuit field. First of all, we want to make sure the chip is indeed radiating at the frequency we want. And unfortunately, it's very hard to directly detect the spectrum at 1 terahertz, as you can imagine, right? So in here, what we do is we put a lower frequency spectral analyzer, which can operate at about 250 gigahertz, and you put it very close to the chip, even though this chip is not designed for having any radiation at 250 gigahertz. But more or less, you have some little leakage there. And you can detect this leakage, and this one is measured to be roughly 253 gigahertz. So this sort of tells us that, okay, this one is oscillating, and it's oscillating at 253 gigahertz, okay? Which means that the fourth order harmonic will be above 1 terahertz. And then you take a very different approach. You take zero biased Schottky diode detector, and that was fed by a Hor antenna, and this antenna now only allows the frequency around 1 terahertz to get in. Okay, so previously you determine what the frequency is, and now you can just measure the power at the desired frequency you want. And then the measured radiated power is about 80 microwatt. Okay, and this is a different measurement which further proves the output power. I think this one is actually very interesting. So this is the measured radiation pattern of this very little chip. And what you can see is because here I can integrate a lot of elements together, and now the 3 dB beam width of this terahertz output is really, really narrow. Okay, so this is kind of like the terahertz laser that I was talking about. All right, so if you still remember this tenths of nanowatt of radiated power from these silicon chips that I just mentioned, now if you look at the recent arts, from our group and also from the other groups, what you can see is, okay, things look really promising now. So we are generating power at around milliwatt level, okay? So this is orders of magnitude higher than what was demonstrated before, and it's still gonna be, larger and larger in the future. So this gives us a lot of, faith, okay, in this construction of terahertz components. So this is another example. I don't go to the details, but essentially you take the same design methodology, which is this multifunctional, electromagnetic structure, and you can also build very sensitive sensor arrays. Okay. Previously, people normally use Schottky barrier diode or MOS transistors as a nonlinear square law detector. You take the incident wave from an antenna, and then you feed it directly into these devices. You turn that into a DC current, and you just measure that as the output. Okay, that is really not sensitive. Versus in here, people can design heterodyne receivers. Okay, where you have essentially you have a radio there. You have local oscillators, and then you have the heterodyne mixing, and then you pull the IF signal out of this, and this becomes very, very sensitive. But previously, the problem is if I were to build a large-scale array for these heterodyne receivers, I simply cannot keep the distance to be half wavelengths that I want. Okay, but now with this multifunctional EM structure, you are able to do this. Okay, so here's some comparison. I won't go to the details, but if you look at this graph, it kind of shows you that on the top, these blue dots are the traditional square law detectors, which can easily scale up, but they are not very sensitive. Versus, on the other hand, you can have heterodyne receivers, which is the same as our heterodyne radios. However, you cannot build a large-scale array of those. But now with this new technology, we are able to achieve a very good combination between sensitivity and also scale of these devices. Okay. Now let's jump to something that is more exciting, which is the integrated systems in CMOS. So in this talk, I will give you one aspect of the construction of the terahertz microsystems. This one is very useful in many applications. Here I just want to talk about one aspect of this, which is based on chip scale wave matter interactions. So as you probably know, wave can interact with some microscopic particles like atoms, molecules, electrons. Okay, and here I show you quite some modalities of this wave matter interactions. Going at the megahertz range, you have a nuclear and electron resonance. Resonance is at gigahertz, and molecular rotation at low to mid terahertz range, and also molecular vibrations and so on. And built on top of these interactions, we can actually have quite some sensors and also some metrology systems. And here I want to focus on this part, which is the molecular rotation inside the terahertz range. And I will show you how we can build gas sensors out of a CMOS chip without using chemical reactions. And also we can build essentially atomic clock, okay, without using very complicated and costly systems and components. This is some of the applications of terahertz systems. So first of all, I want to give you some basics regarding what kind of interactions that we are using in here, and that's called terahertz rotational spectroscopy. So if you think about the structure of a molecule, quite some molecules, they have what's called polar structure, where you have a positive charge on one side and negative charge on the other side, okay? And once you have this kind of a polar molecule, it carries electrical or magnetic dipole, okay? So now if you shine a wave, let's say the wave carries electrical field onto an electrical dipole, what will happen? It will start to rotate, okay? It will exert a torque on top of this polar molecule, and when the frequency of the wave is just right, once it matches the natural rotation frequency of this molecule, you start to create resonance, okay? The molecule will start to absorb the photon from the wave. And then once you do this transmissive configuration and observe the absorption spectrum of these molecules, for example, in this case, it's carbon sulfide, what you can see is you can have a set of transition lines or absorption lines in the frequency domain. Okay, there are quite some nice features about this rotational spectrometer. For example, I love this peak a lot because this peak literally shows you why we choose to do terahertz. You have transition lines in very low frequency, microwave and millimeter wave, but the absorption intensity is very small. Versus if you are able to build a spectrometer in the terahertz range, now you can have very large absorption, meaning that your sensitivity can get really nice, okay? Here I show you some of the molecules that could be detected if you build a spectrometer from 200 gigahertz to 300 gigahertz, okay? So as you can see, many of these molecules are toxic and they could be flammable, but at the same time, they have their very unique frequency feature as their fingerprints. Okay, so if you just scan the frequency and if you suddenly see absorption at this particular number, you know for sure that you have this molecule. Okay, so this is actually called absolute specificity. In the microwave and the terahertz spectroscopy field, that's because these transition lines are actually very, very sharp. Okay, so you don't have false alarm out of this. So how do we build this? This is what people have previously constructed. This is a terahertz spectrometer out of commercial compound semiconductor discrete components. One thing you can see is the terahertz component actually occupy quite some space. And I guarantee you, if you were to purchase, for example, your radio club, if you want to do some terahertz system construction and you purchase these components, this can easily cost you the price of a BMW or even a Porsche. Okay, so that's the sort of scale you should keep in mind, which really motivates us to shrink these electronics down to a chip scale and make it small, but more importantly, make it very affordable. okay? And people have tried some of these constructions, which are also pretty successful. But if you look at what has been done so far, one commonality of the system is that they use a single tone signal, and they sweep this single tone signal across this entire band in order to check what the absorption is, okay? So if you design something in this frequency range, you probably know that the circuit has to rely on very high quality factor resonance, because once you have a high Q resonance, you can sort of recycle power, recycle energy, okay? And that makes things more efficient. But once you have a high Q circuit operation, your bandwidth would not be high, okay? Meaning that your transceivers simply cannot cover a very wide range. And more importantly, because these transition lines, as I mentioned, is very sharp, okay? How sharp it is? It's about half megahertz wide out of hundreds of gigahertz, okay? So you cannot miss them. That means when you do the scanning, you have to have very fine resolution of scanning across hundreds of gigahertz of range, okay? So that's translated to very slow speed. And now if you only use one tone to do that, it will take a very long time. So what can we do if we use silicon chips? How can we leverage the large integration of these silicon chips to do things better? This is one example, okay? Instead of doing this single tone scanning, what I can do is I have two identical CMOS chips, and each chip can generate 10 equally spaced lines, and also at the same time receive the other 10 frequency lines from the other side, and down convert these 10 lines to IF frequencies, okay? So now literally you have 20 lines that are simultaneously scan this band, and number one, you have much faster speed. Number two, if you look at the architecture of this chip, where literally you just use a dedicated transceiver to generate and receive each line. Now this receiver, this transceiver is narrowband, okay? You don't need to cover a very broad bandwidth, and now you can use quite some interesting circuit technologies like high Q resonance, or you can even introduce some feedback, as I mentioned before, to dramatically increase the active gain of these devices. Okay, but once you introduce feedback, normally you don't have a wide bandwidth, but it's okay in here, all right? So for this particular case, we are able to seamlessly cover the band going from 220 gigahertz all the way to 320 gigahertz. Okay, so this is a really broadband coverage, and you can have literally any resolution you want, but normally we scan with kilohertz of resolution. Okay, but again, one big challenge to design such chip is, now I have so many electronics on the same chip. Each piece has to be very efficient and also very small, okay? CMOS chip design is very sensitive to area, because area literally means money, okay? So you need to really shrink the size of these devices. And I won't go to the details in here, but basically, we also introduced this multifunctional EM structure design, okay, to enable this. You use the same structure, as you can see here. You use the same structure, but it performs multiple tasks at the same time. For example, in here, these two devices, with the assistance of these slots, it can take an input frequency and double that and then radiate it out, and also at the same time receive another signal tone from the other side using the same structure, and then down convert it using the transistor's nonlinearity, and then send out the IF signal. Everything inside this little structure, okay? And with that, now we are able to integrate everything together inside a 6 millimeter square area chip, okay? So if you look at the actual numbers, it contains 10 transceivers with built-in antennas, 9 frequency mixers, 40 amplifiers, and they all operate at very high frequencies, and they all work. I think this is actually a very strong message if you compare to other technologies, okay? For these CMOS devices or chips, once you design them correctly, they just work beautifully for each individual of these chips, okay? Then the cost becomes really low. So these are some measured results. So you can see the chip can radiate 10 frequency lines okay? So this is why we call that a comb, and we really don't have any power degradation on the two sides of the band, okay? And also you can scan this thing nicely. This is the fun part, which is the demo, all right? So what you can see is in this demo, I have a gas chamber where I can inject any arbitrary mixture of gas inside this chamber for my testing. And on the left side and the right side, I have two identical chips, which are driven by external sweepable signals. And then I check the output IF signals. And this is what you can see. In this particular case, I inject carbonyl sulfide and also acetonitrile with a certain mixed ratio into the gas chamber. Why do I select these two? Because these two compounds exist inside your breath, okay? And their concentration have a pretty high correlation with your health conditions, such as the glucose level, okay? So the reason why we do this project is because we really want to have a very little and very affordable gas sensor that can precisely tell you what's going on inside your body, okay? So that's why we chose these two materials. And what you can see is this chipset literally just generated all the fine fingerprints of these two molecules across the 100 gigahertz band. If you zoom into these little spacing here, you can see quite some transition lines for two molecules. And if you do the check, each transition line's frequency really match what was measured by the chemists, okay? So which means that now, if this is an unknown gas, I see this lying here, I know I have that molecule inside, okay? Very precisely, no false alarm again. So now you have a chip which can smell. What else can we do? You know, my student, when he was working on this spectrometer project, he showed me some of these measured spectral lines, okay? And when I look at this line, I was like, you know what? This line number one, it's very sharp. Okay, as I mentioned, this is about megahertz level out of hundreds of gigahertz. Really, really sharp transition lines. And also their frequency. Look at how many digits I have in here. It's very precise, and really it doesn't change if you change the temperature, if you change anything around it. Okay, so this is a constant physical variable. This is a physical constant in there. Okay, and what can I do? Well, if I can align my generated frequency tone at the value of this transition line, then I precisely know what that tone is, okay? And since this tone is generated most likely from a phase lock loop, I know what the input frequency of this PLL is, okay? And then that's atomic clock, because now I link my low frequency with this physical constant, okay? And if you think about this principle, this is literally atomic clock. But why do we need such thing? Okay, so here I give you some background information, which shows you some comparison of different frequency references or clocks. So if you can only afford to build very low cost and burn very little power, then normally use crystal oscillators, as you normally do. Okay, crystal oscillators normally give you a stability on the order of 10 to the minus 6 or 10 to the minus 7. Okay, so it's a decent oscillator or decent clock, but it's not so good to the point that you can use it in your cell phone, computers, but you really cannot do that and install and provide the frequency reference for, say, base stations, for the cell phone towers, and also do navigations and do some high frequency stock training, for example. Okay, instead you can use atomic clocks to do this work. But what you can imagine is, atomic clocks is super expensive. Okay, if you can get something like, for example, cesium clock, then you have to spend, again, the price of a car. Okay, and they're also pretty bulky. So that's the normal trade-off you have to bear with. There are some exceptions. For example, people in the past 2 decades have tried very hard, and they generated this, what I call engineering masterpiece, which is a chip-scale atomic clock. Okay, and literally what you're doing here is you use a laser that is very well tuned, and you detect the spin resonance of cesium atoms, and then you translate that into your output frequency. This thing is much smaller, as you can see, and also the power is 120 milliwatt, very low power, but look at the price, okay? And there's a reason for that, because you literally need to have very advanced electrical and optical components inside this little device. Okay, and also there are other problems associated with the complications, such as long-term stabilities, aging, stuff. Now that you have already seen this chip, which can smell, we can actually turn that into a clock. For example, here I use a single-mode waveguide. I seal it, and I put some known molecules inside it. In this case, it's a carbonyl sulfide. And then I use a CMOS chip to generate a certain terahertz wave and couple that into the waveguide. And this wave excites the rotation of molecules. And depending on where the peak absorption happens, I can dynamically tune my output frequency until I align with the peak absorption. And once you have that feedback network, now the input reference frequency of my terahertz phase lock loop becomes directly related with my constants. There's a physical constant here with a known factor. Okay? And now I have a very, very stable output frequency. So this is literally a chip-scale atomic clock, except that here I don't use any laser. Okay? I don't use any heater. I don't use any complicated and costly components. All I need is a CMOS chip and a waveguide. Okay? So we call this molecular clock, and more importantly, according to our calculation, the total volume of the gas you need, and that volume is the ultimate limitation for the size of this clock, is below 10 millimeter cube. Okay, so it's a really small, tiny gas cell you need to build this clock, and CMOS chip is literally, nothing. Okay, it's really small. So now you have a clock that is super small and super cheap. Okay, so we built some lab scale prototypes just to verify this idea. And what you can see is in the measurement, this thing can reach 10 to the minus 11 stability. Okay, which means that if you wait for what is that, 10 to the 11th second, then you can observe the shift of 1 second. Okay, that sort of thing. So it's very, very stable. This is probably a more straightforward representation. So this line is the normal crystal oscillator's output, and this is the one with the molecular clock. Okay, so you can see that over 4,000 seconds, this one literally doesn't have much drift, versus the crystal oscillator gives you a lot of crazy output. Okay. We also checked the other physics of these rotational transition lines, and the conclusion is they are really robust against the magnetic field externally applied, and also if you change the temperature, the drift is also very small. For example, in this testing, if you change the temperature by 1 Kelvin, it drifts by only 10 to the minus 10, okay, without any compensation. So what I just showed you is still some bulky stuff. Okay, it verifies that this molecular clock could work, but it's so far away from being practical. This is what we promised to do. Okay, so how do we know that eventually this dream can come true? Well, this is MIT, right? So if you have a dream, you build for it. And this is what my student eventually built. Okay, so we use a pair of CMOS chips and literally just build everything and shrink everything that you just see, from those photos onto this set of chips. Okay, so this thing can precisely generate a controllable output wave with a certain frequency and couple that wave into the terahertz waveguide. And then this is literally a locking amplifier. Some of you in here probably know that. And this chip dynamically jumps its frequency from at the two edges of this sharp transition lines to do the comparison of the absorption. And in a steady state, the two absorptions are the same, meaning that the center frequency is right in the valley, okay, or in the center. So once you do that, and by the way, this is the package of this chip scale molecular clock. It's about bottle cap size. The actual gas inside is much smaller. The reason why it couldn't be smaller is because we need to hook it up with some other vacuum pipes and the other components. But look at the power. You only need to burn 66 milliwatt of power, and then you get atomic clock, basically. Okay. And here are some measurement results. This is the result of our first prototype. So what you can see is the stability is on the order of 4 times 10 to the minus 10. Okay, so this is not as good as this bigger version that I just showed you. Fortunately, recently we generated the second generation of this chip clock, and that one literally pulled this thing down and get it closer to 10 to the minus 11. Okay. So that's the future. That means in the future, inside your mobile devices, you're able to have a frequency reference that is super, super stable, okay? And if you think about the impact, one instant thing I can think about is navigation. If you think about GPS, by principle, you only need to receive signals from 3 satellites and know where you are, okay? But because your local clock is not stable or is not precise, you have to interact with the 4th GPS satellite to calibrate yourself, okay? And that is why, and this, this calibration process takes some time. That's why, if you turn on your Google map, it takes some time for that big blue sphere to get smaller and smaller, and eventually you know where you are, okay? But with these components, things will get much better, okay? And here I want to show you some of the future stuff regarding this chip-scale atomic clock. Well, number one, if we further push the frequency to half terahertz, which is something that we are doing in our lab, then the waveguide will become so small that you even don't need to have any external waveguide to store this gas, okay? You can actually just carve out the waveguide directly out of the substrate of the silicon. Okay, and then seal the gas inside, and then you're done. Okay, so this becomes truly chip scale because it's literally just a chip. Okay, all right. So, right before this talk, since I know that this is live streaming, I have to painfully remove some slides talking about some recent work in my group. Which actually shows you some more applications and some more microsystems in the terahertz range. Okay, for example, we can use a CMOS chip to perform radar imaging. Okay, and as you can imagine, since you have terahertz wave in here, you have a lot of bandwidth. Okay, and actually utilizing our comb architecture, now our radar can have 100 gigahertz bandwidth. Okay, so it does this FMCW sweeping from 220 gigahertz all the way to 320 gigahertz. Okay, so if you know something about FMCW radar, you can probably translate that into how much resolution you can achieve out of this. Okay, so that's pretty exciting. And another work that we have done so recently is we can build very, very small RFIDs. Okay, if you think about RFIDs, the chip itself is very small, but actually you need to couple the RF wave in and out of the chip. So outside of the chip, you need to have quite some loops and wires, okay? And this kind of packaging really limits the application because it's so big, and also the packaging itself can cost more than the chip itself, okay? Now using terahertz operations, we can literally shrink everything down to a single chip, without any external batteries or components. The size is only 1.6 millimeters square, okay? And that's it, that's your RFID, okay? So it absolutely enables some very exciting applications, and new things are still going on their ways. All right, so let me conclude my talk. I only want to give you some takeaway messages because this is not a highly technical talk. Number one is, in the future when you work with a certain device technologies, you are not supposed to just focus on the material properties or the performance of a single device itself. Okay, you have to zoom out and really look at from the systematic perspective, really look at the big picture. And hopefully in this talk, I show you that even though each silicon transistor might be dull, might be slow and noisy, okay, but one nice thing is they are really collaborative, okay? You can use a bunch of these devices and make them work together on the same chip and perform something that is really, really powerful, okay? And the second message is, even for the device itself, what I just showed you is not the end of the world, okay? If you take a look at the recent advances from Intel, from GlobalFoundries, from IHP in Germany, they have started to show very high-speed devices, okay? For example, the cutoff frequency could be as high as 500 gigahertz for CMOS and 700 gigahertz for silicon germanium HBTs. Okay, so even for these silicon devices, people are pushing those things forward. And in the future, probably you don't need to painfully use this harmonic generation to get the signal you want. Okay, and things will become even more efficient. Thirdly, I have already introduced this two-dimensional terahertz gap. Of course, I don't anticipate that many of you in here will work in terahertz. But what I'm trying to say is, when you work on a certain research topic, don't just focus on some things with a small scale. Okay, you have to really zoom out and really take a look at the bigger picture. Think about what is the general bigger impact that my research could generate. What are the missing puzzles? And let me fill those missing puzzles. Okay. For example, in here, instead of simply focusing on the component level performance, do something on the system. Try some new applications that maybe people haven't thought about. Okay. With that, I will conclude my talk with this picture. Okay. So indeed, we have this gap in here, but now we are using these silicon chips, which essentially made out of sands, to fill up this gap. And hopefully, in a few years later, you can see that this gap could be filled. Okay, so I would like to thank these my students, postdocs, collaborators, and sponsors. And now I'm open to some questions. Thank you.
Have you considered essentially doing like an optical gyro except in terahertz on a single chip?
A very good question. Yes, and actually I had quite some discussions with another colleague of mine, because it will be very attractive to basically observe the shift of the wave, right, that is rotating on the chip, and then turn that into a gyroscope operation. The problem in here is the frequency is, if you look at the equation, okay, the frequency compared to the light frequency is still too low, to the point that with a certain rotation speed, the phase shift is still too small. So small that it will be probably impractical to be detected. So that's the problem. But we haven't tried anything yet. Okay, so that could still be a possibility, but that's a very good question.
Well, I was actually a little curious. So you showed the one slide with like the phased array sort of configuration where you'd have be able to do beam steering. I was just a little curious how you're actually tuning the phase of these frequencies. Is that like the same way we do phase shifters at lower microwave frequencies? Or
well, let me be more clear in there. In here, the signal sources that I have shown you so far, those are not phase arrays. Okay, so we don't change the phase of these sources to tune the beam. For the receivers, they are, okay, because you can simply just change the output IF signal and tune their phase, and then combine them together in a low frequency analog domain so that your response is steered towards different directions. We are indeed working on some components that eventually allow us to do this very high resolution beam steering, and yeah, so just wait, be patient and wait for a few months. It will come out.
In a slide at the beginning of the talk, there was a group of like future applications, one involving teeth.
Yep.
What was that? I don't.
Well, you can basically do some imaging out of some objects. okay? And the selection of this teeth is a very well-designed problem, I would say, okay, because water absorption of terahertz is very large, okay? So if you want to detect something out of your body, that something has to have very low water concentration, okay? And that's why, we choose the T thing here. Sometimes people utilize this feature and they just want to detect the hydrogen level or hydration level or just water contents out of the body. For example, people use terahertz wave to do the imaging of the burn area. Let's say, I get a very severe burn and on my hand, everything's covered by carbon and it's dark, but the surgeon really needs to know where is the area that is truly burned, where is the area that is simply just, get covered by this smoke. And if you use that, if you use X-ray to do the imaging, you just cannot see anything, okay? It's all very good transmission. And this is where terahertz can perform very nicely, okay?
So relating to the application you were talking about with artificial nose, essentially being able to detect gases in a mixture, how sort of generalizable is it to identify a gas based on a frequency? Like, do you have to have just a library of gases and their frequencies, or can you see a new frequency and be able to infer what gas it is?
So I would say there are a few limitations. The first limitation is that, as I mentioned, the molecules have to be polar. Okay, but there are a lot of molecules which are not polar. For example, oxygen, if you think about it, it really doesn't have a dipole moment. If you think about carbon dioxide, it's symmetric structure, so you don't have a polar structure out there. So this is one limitation. However, a lot of interesting gas, they carry the polar structure. Another limitation is, that's something I didn't talk about in here, is that as you saw from this absorption spectrum of carbonyl sulfide, that's a very standard and typical one. The absorption lines are normally periodically located, okay? Sometimes the pattern is kind of periodic, not strictly, repeatable, but that actually offers us to create a window, spectral window, and cover most of the molecules that we want to have, okay, because of this periodicity. However, that window still needs to be large enough in order to cover as many molecules as you want. So in this particular case, when your frequency range is 100 gigahertz, our calculation shows that you can cover molecules, polar molecules, as long as their weight is heavier than hydrogen cyanide, or HCN, which is, a light molecule. But, these are the limitations. And indeed, once you see these spectrum frequencies here and there, you need to refer to the database that people have already generated previously, okay? So there's one database generated by JPL NASA, okay? The other one is generated, or I believe the other one is kind of like a collection of the results in the community, and it's called HyTran. I think it's managed by Harvard University. Okay, so these are the existing database that you refer to. Okay, any more question?
Well, actually, I guess before closing, I do have another question, which is I'm a little curious. So how do they actually generate that database of frequencies? Is that just calculated, or is that based on measurements of lower frequencies that are easier to see?
So I believe eventually these frequencies are verified by experiments, but my understanding is this is a very big area in the chemistry department. Okay, so if you talk to, for example, Professor Robert Field, they have a lot of research regarding how to theoretically predict what the actual transition frequencies is. Okay, they can even predict the shape of that transition line based on the behavior of the molecules. But yeah, I mean, eventually these things are verified by experiments. And The transition lines, well, these data are actually online. So, you can find some online database. You just, select a certain molecule from a drop-down menu and give a certain pressure and frequency range, whatever, and it shows you what the spectrum looks like. It's very cool. Yeah.
Okay. Well, first of all, thank you so much for joining us.
Thank you for having me here.
And thank you all for coming. This is the last lecture of the series this year, but everything's recorded online, as well as lectures from last year as well, if anyone's interested. They can all be found on our website, w1mx.mit.edu. With that, thank you.
Thank you.
This was actually really good.
Thanks. I just hope it's not too researchy or,